Welcome to my video lecture based on Electrical Machine 2, paper code PCE 501. Today's topic is losses and relationship with power of three-phase induction motor. Myself, Pranam Banerjee, Assistant Professor of Electrical Engineering Department, Dr. Sudhir Chandra Mishra, Institute of Technology and Sports Complex. Previously, this institute is known as Dr. Sudhir Chandra Mishra Degree Engineering College, and this organization is under GIS Group. In my previous lecture, we have discussed about introduction of three-phase induction motor and what are the types of induction motor and what is sleep and what is the relationship of frequency with sleep of three-phase induction motor. In this lecture, we will mainly discuss about losses. In case of three-phase induction motor, the losses can be defined into two parts. One part of losses occurred in the core material, another one is in winding, and another part in the mechanical part of the machine. So, if you consider the things, total things, the core material is made of iron. So, definitely the loss occurred in the core material, that is known as core loss or iron loss, which includes hysteresis loss and eddy current losses. And the winding of the three-phase induction motor is made of copper. So, this type of loss is known as copper loss, or we can define it as I2R loss. Apart from these losses, there will be another losses, that is frictional and windage losses. As the motor is rotational one, so definitely there will be friction and there will be windage loss. So these are the main losses of three-phase induction motor. So when the motor starts rotating, there will be steps of power flowing. That means in stator's part, we are giving the three-phase supply, and stator magnetic field is developed, and from there stator input to stator output there will be some losses, and after those losses we will get the stator output, and that stator output comes to rotor input. Now again in rotor part there will be some losses, and after those losses we will get the rotor output or the mechanical power developed. So that is the chain flow of the power in case of three-phase induction motor. Now we will try to develop a relationship between this power flow and between this power with losses relation. So let us consider a relationship between rotor copper loss and rotor input. Copper loss means I2R loss. So, the thing is, this rotor copper loss is basically the I2R loss, and the rotor input is basically the output of stator. So, doing this mathematical relationship between rotor copper loss and rotor input and output, let us consider the developed torque is tau d, and the torque exerted on the rotor by rotating flux. Next one is ns, synchronous speed, and another part is nr, that is rotor speed. So the power transferred from stator to rotor, it will be the air gap power. That means there will be losses, and after that losses, the power output from stator goes to rotor. So the power transfer from stator to rotor is basically the air gap power. So it will be air gap power is defined as PG. So we are writing that omega into tau d. We know that the expression for power can be also expressed in form of omega angular velocity into the developed torque. So the power at air gap equals to omega s into tau d, where omega s is 2 pi ns. This small ns indicates that speed in revolution per second rps. Okay. And when we will represent it by capital Ns, it will represent that revolution per minute in rpm. So the input power to rotor is Pg 2 pi ns into tau. Now the total mechanical power developed by the rotor, it will be Pmg equals to omega r, basically the rotor speed, into tau d developed torque. So it will be again 2 pi nr into tau d, where nr is the rotor speed in rps. So definitely the difference between the power transferred from stator to rotor minus the mechanical power developed will be our I square R loss or copper loss in rotor. Because mechanical power developed means it is the output of the rotor and the input of the rotor is known, that is air gap power. So definitely the difference between input and output will be the loss. So in case our loss is I square R loss, so it is copper loss PRC equals to PG minus PMG. So doing that we are getting 2 pi ns minus nr into tau d. So for getting the relation, we will divide the total I square R loss in rotor with input power to rotor. Then we are getting that is equals to slip. So it will be rotor copper loss is equals to a slip into rotor input. That means PRC equals to S into PG or equals to S into PIR, rotor input. Thus, the rotor copper loss is equal to the slip times the rotor input. The term SPG is known as slip power because it is proportional to the slip for a given value of PG. It is the proportion of the air gap power which is not converted into mechanical power. And also the rotor input is equals to mechanical power developed plus rotor copper loss, that is PIR equals to PMD plus PRC, where PRC equals to S into PMG plus PRC. So in place of that, we are putting that, taking common PRC, we are getting PRC into 1 minus S equals to S into PMD. So from that relation, we are getting that rotor copper loss is equals to S divided by 1 minus S into PMD. That is, rotor copper loss is equals to S by 1 minus S into mechanical power developed by the rotor. So PG equals to PRC equals to PMG. That will be 1 is to S into 1 minus S. From the above discussion, it is seen that once the air gap PG is determined, three quantities may be found from slip and synchronous speed. That is, PRC equals to S into PG and PMD equals to 1 minus S into PG. So developed torque is PG PE by omega S. So from this total relation, we are getting that PG is to PRC equals to PMD equals to 1 is to S into 1 minus S. Now we will go to the relation of developed torque. The developed torque or induced torque in a machine is defined as the torque generated by the internal electric to mechanical power conversion. The torque is called electromagnetic torque. This torque differs from the torque actually available at the terminal of the motor by an amount equal to the friction and windage torques in the machine. The developed torque is given by developed torque equals to mechanical power developed by mechanical angular velocity, that is PMG by omega r, that is the developed torque. Since PMG equals to 1 minus s into PG and omega r equals to 1 minus s into omega s, so we are getting that tau g equals to PG by omega s. That relation is also satisfied for developed torque. Okay. Now we will concentrate on a numerical problem. The power input to a 3-phase induction motor is 60 watt. The stator losses total 1 kilowatt. Find the total mechanical power developed and rotor copper loss per phase if the motor is running with slip of 3%. So, stator input is 60 kilowatt, slip is 3%. So, it will be 0.03 per unit. And stator loss is given 1 kilowatt. So, definitely the stator output will be input minus loss, that is 60 minus 1, that is 59 kilowatt. Rotor input equals to stator output, that is 59 kilowatt we are got. Now for calculating rotor copper loss, we have to do that is into rotor input. So it will be 0.03 into 59, that is 1.77 kilowatt. And as the rotor copper loss we have to calculate in per phase, and this loss we have got in 3 phase. So definitely for calculating it for per phase condition, we have to divide it into by 3 to get the per phase copper loss, that is 2.59. Next one is mechanical power developed. Mechanical power developed will be rotor input minus rotor copper loss, and that will be our mechanical power developed, which is 57.23 kilowatt. Okay. Now rotor on loss, that is slip into rotor power input. So it will be S into mechanical power developed plus rotor copper loss. So it will be PRC equals to S into PM plus PRC. Calculating that, we have got this relation. Okay. Next, another problem, let us consider. The stator loss of 3-phase induction motor is 2 kilowatts. When the power input is 90 kilowatt, what will be the rotor mechanical power developed and rotor copper loss if the motor is running with 4% slip? Slip value is given, that is 0.04. Stator input is given 90 kilowatt. Stator loss is given 2 kilowatt. So rotor input will be equals to stator output. So definitely rotor input will be stator input minus stator loss, that is 90 minus 2, 88 kilowatt. So rotor copper loss will be S into rotor input, that is 0.04 into 88, 3.52 kilowatt. So from there, mechanical power developed will be PM equals to PRI minus PCR, that is 88 minus 3.52, 84.48 kilowatt, that is mechanical power developed. So the total thing is rotor input we have calculated, rotor copper loss we have calculated, and mechanical power developed we have calculated. Now another important thing is to discuss, that is rotor current. Basically you have to imagine that the 3-phase induction motor equivalent circuit is similar like the equivalent circuit of a single phase transformer. So imagining that the calculations can be made that let the EMF E20 is the EMF induced in the phase of rotor at standstill. R2 is the resistance per phase at the rotor. X20 is the reactance per phase of the rotor at standstill, and Z20 is the rotor impedance per phase at standstill, and I20 is the rotor current per phase at standstill. Z20 definitely it is the impedance, it will be a combination of R2 plus JX20. So it will be I20 equals to E20 by Z20. So power factor at standstill will be cos phi equals to R by Z, that is R20 divided by root over R2 square plus X2 square. Now rotor current at sleep. When the rotor is at running condition, then our induced EMF becomes E2S equals to S into E20. So rotor winding resistance per phase it will be R2. Rotor winding reactance per phase it will be 2 pi F2 into L, and rotor winding impedance per phase at sleep it becomes R2 plus JX2S. So putting this value we can calculate the rotor current, that is I2S by Z2S, and power factor R2 divided by Z2S. So these are the important parameters for numerical problems. So according to that we will concentrate on a numerical problem. A three-phase induction motor with star connected rotor has an induced EMF of 60 volt between slip rings at standstill on open circuit with normal voltage applied to the stator. The resistance and standstill reactance of each rotor phase are 0.6 ohm and 4 ohm respectively. Calculate the current per phase in the rotor when at standstill and connect to a star connected rheostat of resistance 5 ohm and reactance 2 ohm per phase. B. When running short circuited with 4% slip. So first condition is when the motor is standstill, and second condition which is running with 4% slip. And our induced EMF is given 60 volt between slip rings. That means we have to convert it to per phase as it is star connected. So definitely when we will convert it to per phase, it will be divided by root 3. Total resistance is 0.6 plus 5 ohm because 5 ohm resistor is connected, and total reactance is 4 plus 2 because 2 ohm reactance is connected. So putting these values we can calculate that current at standstill will be 4.22 ampere. And when it is at running condition, the things we will change, that is EMF. So it will be S into E2. So the value will be 0.04 into 60 by root 3 and 1.3856 volt. And putting the values of Z2S it will be plus, not multiply, it will be plus. R2 square plus S into X20 square. So the value of Z2S is 0.62 ohm. And I2S will be E2S by Z2S, that is 1.3856 divided by 0.62, that is 2.235 ampere. So that will be the currents in both conditions, when at standstill and when at running short circuited with 4% slip. So here I am finishing today's lecture. I have taken this lecture from the book of Ashfaq Hussain, Electrical Machines. Various numerical problems are solved in the book of Abhijit Chakraborty and Sudipta Nath of Electrical Machine, and you can also go through the book of Nagarath Kothari for advanced understandings. And for betterments and better understanding. First, you will start with a basic book like Ashraf Hussain or J.B. Gupta or Mehta. Then go for the advanced part like Bhimra or P.S. Bhimra book or Nagraj Kothari book, and that will be helpful for you. Thank you all. We will again continue on 3-phase induction motor in my next lecture.